Okay, in this section we're going to go through the math of the photoelectric effect, and we're also going to talk about how the experiment was physically run and how to do it, because it's actually so easy that you could run it in your house. All right, so here's what we're going to do. We talked about the work function, okay, and the work function is how much energy is required to break the electrons off of the material, the atom that they're stuck to. Every material has its own work function. For example, sodium has a work function of 2.28 electron volts. Notice we're doing everything in electron volts, which is that teeny tiny amount of energy that we can use. And you can just convert between electron volts and joules by literally taking your number and multiplying it by the amount of electrons. So in this situation, we do 2.28 times the charge in electron, 1.6 times 10 to the negative 31st. Negative 19th, sorry. Okay, so sodium would be 2.8, aluminum is like 4.08 electron volts. You get the idea, you can look it up. Let's talk about another key equation, the energy that light has. Okay, and we briefly touched on this in the previous video, but the equation we're going to use there is H times F. And H is a constant of the universe, it's Planck's constant. Okay, Planck's constant, a few things, notice it's not spelled like the board. Second of all, there's Planck's constant. You can write it a couple different ways. You could do it with joules, which is the top one here, or you can do it in electron volts. Which one do you want to use? It depends on the problem. If you're doing problems where it would be advantageous to have joules, you can just multiply the frequency by this number on the top, and you will get your answer out in joules. If you were to multiply your frequency by this guy on the bottom, you will get your amount of energy out in electron volts. So pretty convenient. You don't have to memorize either of them. They're a constant. They're on the front of your equation packet. And of course, F is just, frequency, which was measured in hertz. And again, this is energy, and what energy you get out depends on which Planck's constant you pick to use. Okay, if you want to knock off one of these outer electrons from the outside of an atom's nucleus, you're going to have to send down the right amount of energy. So in that situation, it's really important to remember that light in this particular experiment is going to act like a particle. So if we have a work function, let's just do sodium here. So the work function of sodium is 2.28 electron volts. So we want to send down that amount of energy to break that bond. So we would have to, so what energy are we getting that from? We're getting that from the light. So H times F would have to be at least equal to 2.28 if we're going to even just break that bond, electron volts. So we could pretty easily calculate that. So we'd put in, we're dealing with electron volts, so we'd want to put in our Planck's constant over here in electron volts. So we would choose the, let's see, that would be 4.14 times 10 to the negative 15th times the frequency is equal to 2.28. Okay, and if we solve, we're going to get the frequency that you would have to have as a bare minimum to break off this electron. Okay, so we get 5.5 times 10 to the 14th hertz. In other words, this is the amount, this is the frequency of light that you would have to send down onto this atom just to break that bond. In other words, just to get this electron to sort of no longer be going around there. Not flying off, just broken off from the atom. It's not really, it doesn't even have the energy to really go anywhere. This is the bare minimum frequency of light. So if you go to any frequency lower than this, even by just a tiny amount, you're not going to break that electron off. So if you went down to like 4.3 times 10 to the 14th hertz, you get nothing. And that's the situation where you're talking about like almost like the AP students are standing in a room and you're raining down quarters. You don't have enough frequency, you don't have enough high enough payment to even break them off. Quick pause here. Sometimes the problem will actually give you the frequency that will help, that will cause the electron to break off. It is called the cutoff frequency. Okay. So in the last problem, we solved for it, but in some situations, they're going to give it to you. It's called the cutoff frequency. We're going to get into why when we look more at the graphs. They also can give you the cutoff wavelength. Okay, so they could do any of this stuff in wavelengths. It could be like, you shone this light down on such and such wavelength. What happens? So just keep in mind, people have a really hard time remembering this. If you know frequency, they go together. If you have one, you have the other. And the equation that ties them together is C is equal to F lambda in cases of light. The more general expression of that is the velocity is equal to F times lambda. You know it because you always know C for light. It's 3 times 10 to the 8 meters per second. So if you know this guy, you can find this guy. Always, always keep that in mind. Now, what's happening is science had a little bit of a difficulty. If you were to just break off the electron, you had just enough energy to, and we'll zoom in here on nature, okay, you were just to break off the electron, okay, it's right there. But you didn't give it any extra energy. It doesn't have any energy to go anywhere. It's stuck there. And it's not like we all have superhuman powers where we can just look down at a metal surface and be like, I see the electrons broken. This is fascinating. And, talk about it at cocktail parties for the next 15 years. We don't have the ability to actually see the electron doing that. So how in the world do scientists know if the electron is broken off? Okay, what they do is this. They send down some light that has a little bit higher frequency than required. Okay, so if you needed, 1.2 times 10 to the 14th hertz, you would send something greater down, maybe 3.2 times 10 to the, 14, 15 hertz. What that does is now you don't just get the electron breaking, but you've actually given the electron a little bit of extra money, or a little bit of extra energy. So it can now leave. And we're going to talk about how a moving electron, which we've seen earlier in this class, is actually kind of easy to collect and calculate over. So in other words, if you're struggling with this idea, if you're thinking of the AP physics students getting broken out of the classroom, if you just send down the exact amount of energy, it's like I gave you exactly $5. So you can step outside the classroom, but you can't go anywhere. In order for you to go anywhere, it's like I'd have to give you, $10, $5 to get out of the room, and an extra $5 to get a taxi and go home and talk about how horrific AP physics is and how much you're going to need therapy for the rest of your life. So now we have a situation where we've sent down a certain amount of light higher than the cutoff frequency. So HV is higher. And now what we've done is we've broken the bond between the atom. We've done the work function thing. And now we have an electron kind of flying off like this. If we knew how much energy it had flying off, we would be able to back calculate exactly how much this mystery work function is. We don't know how much it is, okay? So we could figure that out. So what did they do? They set up a pretty ingenious situation. Can you think of anywhere in this class we had electrons moving at a particular velocity and we could calculate things about that? If you just felt an icy shudder move through your soul and you thought, oh no, I have seen that. That was electrostatics. Oh no, that was the correct answer. You did see this in electrostatics. Electrostatics just keeps coming back to haunt you throughout this whole class and really throughout the entirety of your engineering or physics degree. So what's happening here is they set up a pretty ingenious device. They basically created a little capacitor. And the capacitor is hooked up to a battery, obviously it's a capacitor, but it has adjustable voltage. So you can turn the voltage up or you can turn the voltage down on this thing. And this surface over here is the surface that we're looking at. So what they do is they shine the light down on the surface. And you shine more light than is needed to break the particle off. So you have your little electron, goes flying off, okay? If you set the exact amount of voltage, you could get it so that this guy comes flying up, but he's moving through it's moving through a capacitor. So there is a constant electric field happening in here because we have the positive end of the battery and the negative end of the battery. This is the positive side. This is the negative side. So the electric field lines point from right to left. And it'd be like, okay, what does that mean for the electron? Remember, electrons move they want to move in the opposite direction of electric field lines. So really, this electron comes bombing off there at a high velocity and is actually going to slow down as it moves here. Whoop. And you want to get this so that this electron just barely makes it to this other side. If you could get that, you would be able to back calculate the exact energy this guy had leaving here. You would know the energy of the light coming down, and therefore you would be able to calculate the work function that was holding this guy on there. How could you do that? Remember that if something's bombing along, moving over here, it has a lot of kinetic energy. By the time it gets over here, it would have very little. So how much energy does this little particle here, how much kinetic energy does it have coming off? Well, if you remember from electrostatics, that energy would be, I should write it like this. Okay, that energy would be, kinetic energy is equal to E times V, where E is the charge on the electron and V is the potential difference between one plate and the other. In other words, it would be the exact voltage that you could read on your little power supply here. At this point, you're probably feeling a little bit overwhelmed, so I'm just going to summarize the whole thing. It all kind of comes together into one pretty nifty equation. So in other words, we have the energy from the light coming down is going to do two things. It's going to break the bonds, that's the work function, and it's going to have some kinetic energy. That's not the equation you want to memorize. We're going to make it even easier here. So again, the light comes down, has the work function, but we can calculate the kinetic energy that it had by using the electron charge times the voltage that will just allow it to get to the other side. So we could write this, the energy from the light is H times the frequency of light equals the mystery work function, or in some situations they'll give it to us, plus the electron times the voltage on your power supply. And this is the beautiful equation that you're going to use for like 85% of photoelectric effect. In fact, photoelectric effect, this is really where all the math is. You just need to remember that this part here is showing you the kinetic energy of the electron flying off. This part here shows you the amount of energy required to break those bonds. And this part here is showing you the energy of the light hitting that surface.